This is going to be the cloud computing course or the cloud computing lecture. If you are looking for machine learning, you want to be on all, whatever it's called, 103 over here. This will be on cloud computing. To give this lecture, we have eScience's very own Naomi Alterman, who will take it away.
Thank you, Noah. Hello, everyone. Thank you for coming to our cloud computing tutorial while the very exciting machine learning tutorial is going on next door. I promise that this will get you further in your goals of having robots automate our world for us, despite us not directly talking about that today. So just very quickly, want to introduce myself. So my name's Naomi, as Noah said. I'm a technical education specialist at the eScience Institute. And so broadly, the work that I do is figuring out how to really take the work that scientists are doing and help those scientists learn new skills and new technologies that help them really advance their methodology in their field to do things that they weren't previously able to do. And in a lot of cases, that involves cloud computing. Most of the work that I do at the University of Washington involves cloud computing in one way or another. And so I have the kind of conversation I'm having with you guys today with folks from a whole lot of fields. And so that's why I say, by training, I'm an electrical engineer. And so I have a lot of experience with computer networking, with Unix systems, with getting computers to do things that they don't want to do. But in practice, I really, really like taking complex areas of information and thought and bridging those to other complex areas, be that a compiler bridging code to hardware or a tutorial where we bridge a new subject to people who have their own frameworks and ways of thinking about things. And so what I think we can really take advantage of during this time together is, I have these slides and I spent a very long time on these slides. So please appreciate my graphic design on these slides. But I think that questions and discussions that we can have in this room and over Slack and over Zoom are really an exciting way to, I think, get to know things like cloud computing, because cloud computing really is sort of such a broad topic and can mean so many different things. So just to set expectations for what we're going to be doing over the next hour and a half, a big picture, we're going to be talking about sort of the core abstractions that we use for cloud computing so that we're all on the same page with regards to what that term means, but like at a really, really concrete level. So like not just, okay, you do computing on the cloud and computing has files that you need to also upload to the cloud, but we'll be talking about the details of why you might choose one type of cloud service over another and how you figure out the budget for these things. And if we have time, then I will set up a Jupyter Hub in front of the audience, which is very similar to the one that you guys are using for your other tutorials this week. I also include a link to a guide that shows you how to do exactly what I'm doing, so that if you would like to run your own Jupyter Hub, after this event is done, you can follow those instructions. It's not too hard, especially in the past few years. The people who build Jupyter as a platform have put a lot of work into letting us throw that environment onto cloud computation systems and get lots of power underneath our Python code. But I hope, honestly, that we don't have time to get to the demo. I hope that we have lots of conversations instead, which is what happened last year. Not to hold you guys to a standard of your previous NeuroHackademy attendees. But before we get to any of that, I'm actually interested in what you think the term cloud actually means. And so what I would really love for you to do is post a response to this question in our Slack channel for this tutorial, but hold off on hitting the enter key yet. I want to give you a minute to think of your answer, type it out, and then not send it quite yet. Wait until I say go. I'm going to count down. And when I say go, I want everyone to hit the enter key so we get all of your answers at once. So I'll give everyone a minute to think about this prompt. What does the term cloud mean for computing? And paste it into the channel #Alterman Cloud on Slack. I'll give everyone a minute to open that up. and type their answers out. There are no wrong answers to this prompt, by the way. I am always interested in the sort of a long tail furthest from the standard deviation answers of what cloud means. And we've gotten some very interesting ones in the past. I say that earnestly, they were earnestly interesting. I'm not always sarcastic. Sometimes it just sounds like it because I'm from New Jersey. Okay, I see typing slowing down. So maybe take a minute to finish up what you're writing, and I'll throw the countdown out in a minute. Two words, if it expresses the meaning in your soul, is more than enough. But thank you for asking. Okay, 3, 2, 1, go. This is my strategy to get people to actually answer the question, because when you have people just fill out the answer on their own time, then they'll see that other people have submitted things and they won't bother to type, and we don't want any of that. Secretly, this is all just a ploy to get you used to asking things over Slack so that you'll talk to me, because I want to talk to you. So I see that cloud means sharing, and cloud means the rain emoji. The cloud means doing things elsewhere, and storage and computing online. Ooh, I like this one. The cloud is an aggregate of computational resources and storage spaces, typically very huge, very efficient, shared with many people, so they are able to simultaneously perform computation. There are a lot of points that I really love about that one. It draws like the scale aspect of the story and also the collaborative aspect of the story together. Ooh, I also love this one. Is it like a group of random computers all working on something together? That is, I think, a very accurate way of looking at what it is, no matter how much their marketing says otherwise. It's a powerful invisible machine that's up in the sky that can compute a big data set. And Noah, I will call you out by name. Noah says that it is whatever compute resources I'm using that aren't local and whose specifics I don't or can't know very well. I really like that one because it's highlighting that one of the things that the cloud is attempting to do is keep us from having to worry about specifics of how we are using our computers. They are handling that for us in theory so that we can do more complex things than before. In practice, of course, it's not quite that nice, but I think that all of these answers are getting to really, really good different aspects of what we're talking about today. Global networks of servers, distributed computer systems. Y'all are on point. This is good. All right, so given all of your answers, I think that none of this will come as a huge surprise to you that what we're talking about today is not Dropbox. But instead of that, I'm going to still go into a little bit of detail about what we're talking about here. So when we first heard the term cloud, long before we actually started using it to do computation, it was being sold to us as a product. And specifically, the thing that we were consuming was we would have a computer, we would run out of disk space on that computer, and so we would put stuff on an external hard drive. Maybe you'd put it on several external hard drives when you ran out of space. Maybe you'd make a backup copy. There are multiple copies on some of those hard drives. But eventually there's an earthquake or something, and you would lose all of your storage. At which point you say, is there any way I can pay someone to solve this problem for me? And that's where this first round of cloud businesses showed up. So I think Dropbox is one of the early ones. Google Drive is a storied competitor, and Microsoft has OneDrive. These are all examples of a service that does a thing for your life that you can pay for, and it does it with secret invisible computers up in the sky. Someone somewhere is making sure that your files are backed up and accessible whenever you need them, and accessible easily on multiple continents so that it's relatively easy to fly to Indonesia and load the same files that you were working on in Seattle. And you pay a subscription for this because the truth is, as much as we like to think that digital archives are solid and don't change, it takes a lot of work to make sure that a system stays up and maintains itself over time. If you want to keep a file for posterity, don't leave it on a CDR and don't leave it on a flash drive. It will decay in both of those places. I think archivally, the best place to put files for your own use is probably on Dropbox, because while you pay them money, they will make sure that those files don't get corrupted. But this is not what we are in this room to talk about. What we're here to talk about is cloud computing, which is to say, if you are running code on your computer and you run out of compute power on your laptop, I was just talking to Noah about the sort of machine learning work he does. And so how long did he say it would take to run on your laptop? Like 8 hours?
8 hours at least.
Yeah, so like half a day to train a machine learning model on a powerful MacBook. Versus moving it to a computer that has like hundreds of CPU cores where it will take 10 to 15 minutes. That's a much more reasonable order of magnitude of time to be working on algorithms that you care about. The problem with using these really big computers, though, is that you have to be in a department that has the purchasing power to buy and maintain these things. And you need physical space to maintain these things. One of the problems we have at the University of Washington is that we actually physically don't have that much space in our on-prem facilities. You'll hear the term on-prem a lot to refer to computer racks that are on premises. And so with these computers, you might log into them remotely, run your code, or maybe you have an IT administrator that has a job submission system like Slurm or some other branded name. And you can do your computing. But if you don't have access to one of these supercomputers, then you have to rent your time on it from somewhere. And so there are national research programs like the ones run out of San Diego Supercomputing Center that let you rent really powerful computers for some amount of money, or for some NSF awards, gives you like credits that you can use. But ultimately, the commercial marketplace has realized that they can provide computation on these things as a product to you the same way that they provide storage to the much wider array of people who don't do computing, but they have files they want to store. And so that's where we begin to see products like Jupyter Hub, the one that you guys are using for NeuroHackademy, or like Google Colab, where you can open up a Python notebook. You don't know what computer is running the Python notebook. It's somewhere out in the universe. It's not on your lap. Posit Cloud used to be RStudio Cloud, but then RStudio decided that they wanted to go the generic route and be able to do everything and anything. Now they're called Posit Cloud. But even still, this is not what we're in this room to talk about, because as a teacher, I've tried to train myself to not call problems trivial, but it's trivial. If you go to Google Colab, you can run Python code on a computer that's faster than your computer, and that's it. But you don't have that much control over how much faster that computer is than your computer. And you certainly don't have control over how your data is being stored in those notebooks, or how those notebooks are being shared with your collaborators. You can pay Google a little bit of money to do that for you, to give you options. But ultimately, these are still consumer products, which are defined by product marketing teams that don't really want to give you that much choice about how you use them. And so what we're going to be talking about today is how these services are built. the underlying building blocks that allow Google to provide Colab or allow NeuroHackademy to provide you a Jupyter Hub. Because if you know how those work, then you have a lot of agency and power in being able to set up your own computational systems. And effectively, given however much money you can get from a funding agency, you can find the computers that will perform your work for you. So today we are going to be talking about, and I don't like this term, but it's the one that has been like becoming more and more common. We're going to talk about the public cloud, which is to say it's the cloud of computers that build these consumer services. And that public cloud is currently a triopoly. There are three main big cloud providers. There are other smaller ones that are beginning to get market share. But broadly, when we talk about the public cloud, when we talk about cloud computing, we are talking about Google Cloud, Amazon Web Services, and Microsoft Azure. And the reason why it's called the public cloud is because I want to say around 2003, early 2000s, Amazon realized that they had huge server farms that were being underutilized. And so they could make available to the public web servers that they were not using for a rental fee. And it turned out that was a really good business model. And so because Amazon was the first one to pursue that model, they were sort of the leader in time, and they have the biggest market share now. But all free cloud platforms are at this point roughly competitive in most ways and have their own perks and benefits that make it easier to use one or another. But so these are major tech companies that are making their tech infrastructure available to us, the public, for some amount of money exchanged. Or in terms of research, you can often find academic credit programs where it's sort of, I've heard people refer to it as funny money. They will give you like $100 in credits to use on Azure. And what that actually means, you know, it gets into like business details about like how much it actually costs them to rent a computer out to you versus what they're providing to you. But, you know, all that really matters to us is if you sign up for Azure with a .edu email address, they'll give you $100 of credits that are good for some amount of time. My guess would be like a year. And you can use those to perform cloud computation. Quite a bit. You can do quite a bit for $100. So we're going to be taking a really close microscopic look at what we can do on these three platforms today. And this is what we're going to focus on. And so as for what exactly you can do on those platforms, I want to frame it in the context of what we can do with consumer services. So if we talk about Google Drive and Google Docs, we can create Word documents that we collaboratively edit together. We can create spreadsheets, and we can create slide decks like this one. This one's running on a consumer cloud service on Google Slides. And I can share any of those documents with you guys, and you can edit them and view them, all that great stuff. The building blocks of a consumer computational service like the Jupyter Hub that you have access to are Python notebooks and Unix terminals. So you can open up terminals and run commands, do things like that. Maybe there are also the ability to run Python scripts that are not in notebooks. But like these are the building blocks of, you know, what you actually do on this service. And so at least when I first started learning how to use the public cloud, I wasn't really sure what the building blocks actually were for AWS and for GCP. And so we're going to go through some of the most common ones, but I'm interested right now in doing an interactive exercise. I want us to brainstorm as many cloud building blocks as we can. And unlike the previous prompt where I had this countdown 3, 2, 1, with this, I just want you to send as many as you can think of into the Slack channel. Doesn't matter if you see other people send the same thing that you're thinking of. I just want us to send as many different cloud building blocks as we can into my channel. And I'm going to make it really awkward and silent until I see enough of them show up. I'm not going to move on in the slide deck. And the reason I like this exercise is because you get the obvious few out of the way, but then you really have to rake the bottom of your brain to say, okay, what can I rent from a data center? What do I do with computers? So just to remind you all, when we talk about building blocks on Google Drive, we're talking about docs and spreadsheets. But if we're talking about renting computers from Amazon, what are the things we're paying money for? What are the building blocks? Okay, I see some showing up in Slack. Oh, Tom, I like the way you phrased this. It's not that we're renting storage, it's that we're renting disk space. I don't know why, there's something about the phrasing of that I really appreciate. I think there's like a small tonal difference, you know, like, I don't know. Ooh, supercomputers administration. Yes, they're actually, it's sort of a hidden cost sometimes, but there are a lot of opportunities to pay money to have more administrative power over how you share compute resources with other people. Databases, good one. Comfort. Software licenses. Token of using some functionalities. Headache, it's fair. See virtual machines, that is the classic one, yes. Though I see someone mentioned time as a building block that we can rent on these things. There are pricing models that charge you effectively for, you know, the amount of seconds that your computation takes rather than renting a machine. Ooh, security, that is a great building block, yes. And that's a building block that we run into a lot when we talk about privacy sensitive data, like data sets that have HIPAA compliance regarding them. Those are things that all of the cloud providers do think about, and you can secure, but you really have to think about those as like an object that you are paying attention to. Networking, parallelization, data recovery. Yes. One of the solutions architects at AWS told us that one of the biggest issues they deal with in customer support is ransomware. And I want to clarify here that this is a big problem whether you're on the cloud or not. Is just ransomware as data loss is a really big problem. And so being able to recover backups of your data given catastrophic situations like an attack, a cyber attack, or just like a crash, it's really important. Cooling for CPUs and GPUs. Cool. Can I get one more weird one? I want someone to really squeeze, like wring the towel out. See, people are thinking, people are typing. Well, people are not typing. People have stopped typing. Protection from flood/civil unrest. Yes. And I will actually genuinely, yes, that metaphorically is on my next slide in the form of data centers and regions, because you can geographically distribute where your things are. And that's something that you really can't as easily do if you're managing things on premises. All right, thank you for doing this activity with me. So I think you're going to find that the ones I show on this slide are going to be a lot less interesting than some of the ones that you all brought up, but I just can't help myself getting everyone to brainstorm like that. So the main building blocks that we talk about, some of you have mentioned, are virtual machines, or more generally compute, the ability to run computer code that produces output. And so in Cloudland, those are called virtual machines or VMs. On AWS, those are called EC2 instances. It stands for Elastic Compute. I don't know what the 2 means. On Azure, they're just called virtual machines. On GCP, they're just called compute, I think. And separate from the computers are storage, because virtual machines do have virtual hard drives in them. But you can imagine sort of if you need to store more than your laptop can fit on its hard drive, it's a lot cheaper for you to buy a thumb drive or an external hard drive than it is for you to buy a Lenovo approved internal hard drive that you have to open the case up and like swap out the hard drive and like throw the old one out or put it in a shredder if it's data sensitive. Same thing goes for cloud. There are a lot of different ways to store data beyond just what fits inside of the hard drive of a virtual machine. And so there are a few different terms for that in Cloudland. We talk about file storage. That's what we traditionally think of as like a thumb drive is like a file store. We also have something called object storage that we'll get into in more detail in a bit. And then there are a bunch of brand names for all of these things. You'll notice that GCP, Google doesn't have a bunch of like terms on this slide. That's because Google tends to not come up with brand names for things the way that Azure and AWS do. So on AWS, hard drives are called EBS, Elastic Block Store. Networked drives are EFS, Elastic File Store, and object storage is called S3, which stands for simple something storage, simple storage solution. I don't know. On Azure, they decided to get cute and they called object storage blob containers. But most of the time when we're talking about cloud computing, we're talking about some form of virtual machines and storage. I'm going to venture to say object storage, which takes a little bit of learning to figure out what exactly it is and how it's different from what we normally think of as file storage. But these are the two big ones. These are the equivalent of your Word documents and your spreadsheets, or your Python notebooks and your Unix terminals. In the public cloud, we've got compute, we've got storage. And then just as important, but sort of less actively interactive, are these other ones. And so we have this notion of networking, which some of you brought up. So you don't have to think about computer networking when you use the public cloud, but you do have the power to control how all the computers are connected together and how they're connected to the outside internet, which can be useful for, say, security purposes if you have sensitive data that you don't want connected to the outside internet, but you still want to be able to access. A pretty common pattern will be someone will have a very secure front-facing computer that is in the cloud that is connected to the public internet. And then all of the machines that actually do computation or have data on them will be on an internal cloud network that is not connected to the internet. And the only way that they can SSH, remote connect into those internal computers is to remote connect into the gateway computer that's facing the edge of the internet. And from there, remote connect to one of the internal computers. I just had a call with a customer about this the other day because someone hacked into their VM and used it to attack other VMs, which is sad, but better than it could have been, because sometimes they try to create extra VMs so that they can mine Bitcoin. And that's when you lose money, which almost never happens. I'll mention, there's a slide that we'll get to where I'll mention the one place where that's dangerous, but it is not likely to happen to you. We also have a notion of users and security, which is not the same thing as who can log into a virtual machine. A virtual machine runs a virtual operating system like Linux or Windows. And so you can create and delete user accounts on that the same way that you create and delete user accounts on your laptop. When we talk about users and security here, we're talking about who has the permissions to create a new computer or to create a disk drive with a whole lot of storage in it, or to delete computers and storage. You can think of users and security for cloud as like who has the keys to the computer lab and the debit card that they can order machines from CDW. And the term that you'll see pop up across all the cloud providers is called IAM, Identity Access Management. I have no idea how they all settled on that term. Like, that's the one thing they all agree on, is that privacy and security is called IAM. And so once you start using the cloud, will actually become pretty familiar with IAM, because by default, things are very locked down. And so you'll try to create a virtual machine and you'll get an obtuse error that's like, user does not have sufficient IAM role. And you'll have to like go, okay, well, that means I've not given myself the rights to create a new machine. So I'll go and create a new machine. Or I'll go and give myself the permission to create a new machine. And then it'll say, user does not have permission to create network. You'll go, okay, I need to give myself the IAM role to create a network for the machine to exist in, and so on. I think that that's probably the biggest learning curve, is dealing with IAM. And it's not the kind of thing that's like too easy to screw up. It's just the kind of thing that gets in your way a lot. You can think of it as sort of like when you try to install software on your computer and it like pops that window up that's like, do you trust this software? Do you really want to install this? And you have to like find the yes button. It's like the cloud equivalent of that. Another abstraction that I really like to think about here are locations. That is to say, where in the world physically these machines are located. And this could be really useful if you want to, say, protect your computation and your data from a climate-related disaster like a power outage or an earthquake. Businesses also care about location in terms of making it lower latency to access their data. So like Netflix cares a lot that they have servers in every continent where they have customers, because they don't want all of their movies streaming from North America to Australia. They want to make sure that the movies are in both places. This shows up for us because if we have a large data set, we don't need that data set on every continent, but we want to make sure that our computers are located on the same continent as our data set, or in the same data center, the same physical zone. And the clouds do give you that level of visibility into that kind of thing. So they don't tell you where the building is, but they do tell you whether your things are physically in the same building or not. And then the last thing I'll just mention briefly is this notion of platforms as a service, which is to say, if you want to create a database and you don't want to create a virtual machine, install the database software on the virtual machine, get all of the operating system stuff configured properly, lock the VM down so that people can't log into it that easily, then network it and connect it to all the other VMs. If you don't want to worry about that, you can pay Amazon to worry about that for you. So they're providing a database as a service. And so we see that acronym show up quite a lot, DAAS, database as a service, or MLAAS, machine learning as a service. I generally don't teach that much about how to use those because they are so application specific and vary so much from one cloud platform to the next. So that's the kind of thing where you can save yourself some time and you can save yourself a little bit of money potentially by learning how to use Amazon's machine learning as a service. But it's not practically feasible to really cover most of that in an intro course. But if you're interested about specific applications and whether there are more efficient and quick ways to do it on the cloud than like just renting a blank slate computer, then come talk to me afterward and we can see if we can hook you up. Oh, thank you, Noah. S3 stands for Simple Storage Solutions, apparently. Does anyone else have any thoughts or questions about this before I move on to sort of zooming into VMs, talking more about this? Also, feel free to speak up in person. Yeah. So the question was, why does Amazon use names like these? I don't know, as a corporate culture, they like seem to generally, I think that like Amazon has like 9 billion brand names for everything. So their notebooks as a service is called SageMaker. They have an alternate virtual machine service called Fargate. Their networks are called VPCs, virtual private clouds. I think that they like, actually, here's my hunch. I think that back when this was a small part of Amazon's corporate structure in the early 2000s, it was a bunch of dorks who could get away with whatever they wanted because the administrative structure of Amazon wasn't paying attention to them that closely. And then by the time AWS actually mattered to their bottom line, it was too late to change any of those names. Whereas when Azure first showed up, it was a little bit further down into the cloud mattering. And so they like put a lot more thought into the marketing of all of these things. That's my hunch. I don't know. The thing that I have trouble with in sessions like this is I have a lot of opinions and hunches about things like this because I work with all the cloud platforms sort of equally so much, but I don't want to put them on the record. So I just have to abstract them a lot and say some cloud platforms don't bother making their interfaces easy to use because they have a very large market share. Have no idea who that could be referring to. Other cloud platforms don't have easy to use interfaces because they don't have the engineering capacity or time to make that happen. So I want to make it clear that like all of these cloud platforms are good options for your work. They just do have different rough edges and different smooth, easy bits. So zooming into virtual machines a little more closely. When we talk about VMs, we are talking about computer hardware and computer software, virtual hardware in this case, but it still has the traditional parts of a computer that we are taught about when we are first introduced to these things. So computers have a CPU that crunches numbers. They have memory, which they use to store what's going on. They can have GPUs attached to them, which are accelerated computing units that are used for machine learning. And they have some kind of disk storage so that when you turn them off, you are able to keep what you were doing on disk so that it's not wiped away and deleted the next time you turn the computer back on. And so we refer to the hardware of a virtual machine as an instance type because we're talking about a virtual computer. We call that an instance of a computer. It sort of gets at the fact that these things are conceptual rather than real. But an instance has a specific type. And if you want a bigger, more powerful computer, you need to seek out a different instance type than the one you're currently using. Separately, the software installed on that computer is called the image. And this term comes from traditional information technology and IT provisioning. The image is all of the stuff that is installed on the computer when you first turn it on. At that point, you could start changing things and screwing around with it. But usually when you create a virtual machine on the cloud, you don't install the operating system from scratch. It has Linux or Windows pre-installed on there for you. You can even get a virtual machine with Mac OS, but then you have to pay a licensing fee per hour for that. And that makes the cost like twice what it is for everything else. Not worth it. So the general idea with virtual machines is that if you are doing work on the cloud, if some code is running, it doesn't matter if it's a database as a service or a Python notebook as a service, or you're using the Jupyter Hub for NeuroHackademy. Ultimately, there's some VM somewhere that is doing that code work for you. And the fact that it's there doing that code work means that it's accruing charges. And the way that VMs are billed traditionally is by hour of on time. So if a machine is on, then you are paying an hourly rate for it. And then when you turn it off, you stop paying that rate. You still pay a little bit for the storage, sort of indefinitely, but it's an order of magnitude less than what you would pay for the compute itself. And so the idea here is that for 8 hours a day, if you are interactively using a virtual machine in the cloud, then you are paying effectively for 8 hours of compute time. Then when you turn it off, you are not paying for that anymore. Then when you come back in tomorrow, you turn it on, you're paying for it again, so on and so forth. When you turn it off, it's really easy to make the machine bigger or smaller. And this is where it begins being worth it to think about cloud computing instead of writing a line item budget for buying a bunch of Dell laptops for your lab. If you need a very powerful computer to do some work before a paper is due, then you can rent it for a week or so. and then resize it back down to a much smaller computer to do the rest of your work, and only pay for effectively the amount of computation that you actually need, rather than purchasing a computer that you'll have for 5 to 10 years. People that like thinking about money and stuff talk about this as operational expenses versus capital expenses, which is to say, as you operate on these things, you're paying for them rather than putting capital in upfront. And so if you ever talk to IT people about the cloud, this is how they think about it. It's in terms of CapEx versus OpEx. And I think the most important thing to keep in mind about VMs, this is what my boss says, who is our cloud and general research computing director at eScience. He says that you should treat virtual machine as cattle, not pets, which I think is a pretty brutal metaphor, but I mean, it's kind of accurate here because I treat my laptop like a pet. I love it. I have not put any stickers on it because it has a very beautiful glossy matte coat and I don't want it to get damaged. I make sure I put it in a sleeve when I go home at the end of the day. And if it fell down, I would be heartbroken. But my virtual machines, I will create and delete them like that. Like if I install something wrong, I'll just delete the virtual machine and create a new one. It's like I took it out back and just killed it with a shotgun. The idea here is that it's trivially easy to create new machines. So if you're ever not sure why something didn't work, or if you ever need to do more computing than you currently have capacity for, just create a machine, do the work you need, and delete it when you're done. If you really kind of need to do specialized setup so that you have the environment set up just the way that your code needs, then you can create a new image based on the way your code is configured, so that every time you create a new VM, it just starts up exactly the way you need it, but you still can delete it like that. The idea here is that we're treating them as an interchangeable resource rather than a computer that we're going to give a name to and remember when we go home at the end of the day. And so here's just an example of all the different types of virtual machines that we could rent from Amazon. This is a tiny, tiny list. I chose it just because I think it highlights how varied the different machines are. So for 37 cents an hour, you can rent a machine that has 4 CPUs and 32 gigabytes of RAM, which is roughly the same as this laptop sitting on this desk. 37 cents an hour. So multiply that by 24. That's however much it would cost to run for a day. I can't multiply that by 24 in my head. On the other end of the spectrum, we have a P4D 24X large, which costs $32 an hour. So that is like orders of magnitude more expensive than this other machine. But instead of 4 CPUs, it has 96. And instead of 32 gigs of RAM, it has a terabyte of RAM. Am I doing that right? 1,000 gigs? Yeah, that's a terabyte of RAM. Whoa, that's the kind of thing that when we were talking about Noah's machine learning model taking 8 hours on his laptop and then 10 minutes in the cloud, that's because he is renting a machine that costs $32 an hour. And, you know, if he rents it for an hour, then he can train his model like 6 times and, you know, get a lot of science out of that. And so the cloud looks prohibitively expensive if you look at this in terms of purchasing this $32 per hour machine indefinitely. You could say, well, running this 24 hours a day for a month would break my budget, but you're not running it for 24 hours a day. You're running it for like 1 or 2 hours a week. And you're planning carefully when you're going to turn it on, put your code on it, and get the stuff out of it. So that's where doing this stuff can really begin making sense financially for your research lab. And in terms of, you know, choosing what size of virtual machine we need, it's not necessarily the case that a bigger VM is better, which is to say, pay more money for more of everything and your code will run faster. The reason why I want to emphasize this point is because we work with a lot of researchers who really want to just throw money at the problem and end up having very large research budgets when they don't necessarily need to. And so I want to briefly talk about sort of a general CS optimization strategy, which is to say that broadly, when you run code, it either needs a lot of RAM or it needs a lot of compute. If you think about this in terms of people, this is the difference between a person that can remember the name of everybody at this conference versus someone who can solve a Rubik's Cube in 2 seconds. Maybe there are people who can do both of those things, but computers generally fall into one of those 2 categories, not both. And so what you want to do is figure out which of those resources your code really needs. If you're operating on a large data set and you need to cross-reference things from one side of the data set to the other all the time, you need a lot of memory. On the other hand, if you are doing some sort of numerical computation for a simulation, you're doing like fluid dynamics modeling or something, then you're going to want a compute optimized computer because you're going to be crunching a lot of numbers. You're going to be doing a lot of multiplication at the end of the day. And so no matter how much memory you have, it's going to all depend on how fast the little processor can go. And so it's useful to think about which of these 2 things you need before you start buying cloud machines, because this can really help you go from a machine that costs $32 an hour to a machine that costs like $4 an hour. And that can be a really huge difference when you multiply these things out by, say, like a few months or something. So I don't want to get too deeply into this, but I threw some examples of how you would profile your code. Profile is the term we would use to figure out what the needs of your program are. Here are some Linux commands you can use to look at the memory usage and the CPU usage on your laptop or on a virtual machine. You can run all of these in the Jupyter Hub that we have for NeuroHackademy. So as you're doing other tutorials and as you're doing your projects next week, keep these in mind. You can measure how much memory a given cell of Python code requires to run by putting this at the top of the cell. You can see how much of the CPU is being utilized while a big intensive piece of Python code is running. If you start your notebook and then in a terminal, in a different tab, run the top command, which will show you how much CPU is currently being taken up by all of your programs. And based on this and a lot of art and magic, you can begin getting a sense for what your code needs, and then from there, make choices about what type of virtual machine to rent. And in terms of the virtual machines that are available, there are like 9 billion different instance types across all the different platforms. They have intensely confusing names, and I did my best to sort of select the different series that are there. So like, in terms of a machine on AWS, the T series is a generic virtual machine. It has like a reasonable amount of compute and a reasonable amount of RAM. So a T3 small is like a tiny computer. A T3 extra large is a very powerful computer. Whereas a C small is probably more powerful than a T small because it's compute optimized. It has more CPUs in it, and they're putting more of that money into the compute ability of this machine. So on and so forth. So I included links at the top of this table. Each of these links goes to a different page that on each cloud provider that describes what all the different virtual machine series are. Generally, though, I think that when people first start using this stuff, they're not thinking about virtual machines at this level yet. It's not of value to you to worry about this yet. And so if you really just want a quick start on these clouds, these are, I think, mid-range reasonable computers that can run most Python code and do like serious computational tasks. And each of them will cost you about $2 to $3 to run for a day. So AWS is T3 large, Azure V2, V5, and GCP is N2 standard 2. There we go. That's it. When you have to create a virtual machine, they'll be like, which instance type do you want? Choose those. It's good. In practice, if it's not big enough, what you'll find is the machine seems to freeze up. So that's when you know if the machine just like locks up while you're doing something. Okay, that's when you like stop the virtual machine. You look at what the memory usage was when it locked up. You look at what the CPU usage was, and then you try using a larger machine. And you go on like that until you find something that's big enough to run your code. So we've got another prompt, changing the context here. When you're really focused on work that you're doing, how do you recover from interruptions? In other words, we're interrupting this flow of talking about virtual machines right now with the prompt. So like when you're really focused on your work and then someone like calls you out of the room because the water heater exploded or something like that, when you return to your desk, how do you deal with like getting back into the work you were doing? How do you keep track of what you were interrupted by? Respond in the Slack channel in like a minute. I'll do the countdown again. How do you deal with being interrupted? All right, take a minute to finish up what you're typing. Three, two, one, go. Nice. Make myself a cup of coffee and get back to my focused mode. Take notes before I stop my work. And take time to remember where I left off. Maybe you hadn't taken notes before, but you can rederive what you were doing. Search for my spot and possibly get distracted by other problems. Logs. Keep track of all tasks that have been done and plan to do in the future and navigate based on those records. Set priorities on what I need to focus on first, and then I tell myself I can deal with the interruptions later. Oh, nice. Noise canceling headphones. I reread whatever I was doing last and try to pick up from there. Some of us just cry. Extremely reasonable. So the reason I'm asking you this prompt, aside from the fact I just want to keep you awake on this afternoon, thank you, by the way, for spending your afternoon with me here, is because I want to talk about an exciting new cloud technology called preemptible or spot instances. And the idea here is that rather than a traditional VM that costs some amount of money per hour, maybe there are some sad computers in the corner of the data center that no one's using right now. So you could walk up to Amazon and go, hey, I'll use those, but you'll have to like charge me much less than you would normally. And Amazon will go, well, we're just paying for the power to run them right now. So yeah, okay, sure. We'll accept your lower price. And so this is called a spot instance or a preemptible virtual machine. The problem with a virtual machine is that though it can give you a huge discount, and I'm talking like up to 70% off of the normal hourly rate, that's 70% off of how much it would cost to run that $32 an hour computer. We do have to bid on that rate. We have to convince Amazon that it's worth it to sell that compute time to us for a very low cost. So if someone else outbids us, or if the capacity goes up again, like enough people want to pay the full rate that they don't have spare machines sitting around anymore, then we get evicted And so like the prompt, whatever you're doing, you will have 30 seconds to 2 minutes to finish up before they turn your virtual machine off and you get kicked off. You're free to create another machine at that point. But the idea is that whatever was running your code before is no longer running your code now. And you had a very small amount of time to sort of get off of the machine. In practice, the amount of time is so small that what you really need to do to utilize these things is to have a piece of software or write your code so that it expects to get interrupted at any given moment and can pick up later once it is allowed to get back on the machine again. This might seem like it's kind of prohibitive, but you can do so much with so much less money by using spot instances. And I have some links in this slide deck to software that will let you do that. A lot of machine learning workloads have been optimized to be able to do things like this. And so just to give you a sense of like how much these spot instances can really help, this is the price ratio for, this is actual data that a third party recorded for the ratio between how much spot VM costs versus its equivalent on-demand cost. And each of these series, each of these lines are for different data center regions. So at any given time, a machine might cost more, say, in like a continent where it is daytime and people need the machines versus a continent where it's the middle of the night and no one is on the internet renting them. There was a price spike recently this year. The blog post was actually trying to be a naysaying doom-pod blog post and say that spot instances are dead forever. In practice, the spike has gone down a little bit since then, so I don't know. It's complicated, but it can be worth it to figure out how to use these systems. And in terms of eviction rates, this was the same blog post, said they ran 5 million spot instances and they recorded what percentage of them were booted off within 10 minutes of being turned on. And you can see that it's like pretty good. That's like much less than 1% of 5 million. So it's still quite a few machines got kicked off within 10 minutes. But the idea here is if you have something managing your computation for you, then this can be a pretty good deal.
Is there any indication that the reason for those spikes is due to large language models?
That is a great question. Noah asked if there's any indication that the reason for these spikes is because of large language models. My guess would actually be no. I mean, I think it's like very possible, but I think that there is a combination of hardware pricing and also the tooling for using spot instances getting better. That makes it more practical to actually use these things. But I think as with most things that deal with financial markets, none of my hypotheses have ever actually like seems to correlate with what the reality is. Like the time that I thought that my stock in the startup that I was joining was going to be worth so much because the startup was so great. It turns out you can be great and still not worth that much money. Anyway, if we want to use spot instances, there is a lot of software that can help us with that. There are complicated, heavyweight HPC managers like Open On Demand, which we can use to create our own private high-performance computing cluster. I think some really cool tools that are beginning to show up and get major use are things like SkyPilot, which is coming out of Berkeley's Skylab. And that is a tool you download onto your laptop that you can use to submit your code to run on whatever cloud is cheapest at a given moment. And it is capable of using spot instances. So it can, resubmit your job if it gets kicked off of one cloud, submit it to another one. Dask, which is another tool, this one is Python centric, is really good at distributing computation across many computers. And because it's many computers that are running your code, any small handful of them could get kicked off at any moment. There would be others around that could take the place. So this is my pitch to you that it might be worth paying attention to. Once you are using the cloud and you are familiar and comfortable with it, this is the way that you can save a lot of money and still do quite a lot of computation. Now switching gears again, I'll talk about storage. I guess before we dive in deep about storage, I'm interested about what you all think of my spot pitch. Does anyone have questions about this? Because at least when I found out about it, I thought, I think it's like there's a bimodal response. Sometimes you think this is too good to be true, and other times you think there is absolutely no way that I could write code that could deal with being like randomly stopped halfway through. Yeah.
I guess what are those like best practices for writing that code?
Yeah, thanks for, so that's a great question. So what are the best practices for writing that code that can get interrupted? So the term of art that we see show up in a lot of places is called checkpointing. And that's the thing that machine learning workloads are naturally very good at, because machine learning is an iterative process where you try modifying some parameters, it makes things better or worse. But regardless, you can checkpoint and return to that version of the model at any given moment and keep training it beyond that. If we're not doing machine learning where checkpointing is built into it, I think that the way to think about writing code that can be preempted is that you want to be able to store the global state of your program in such a way that it's very easy to write it to a file on a hard drive and load it back into the program from the hard drive. And so a practical example of this might be if you're writing code that has a bunch of global variables that control what stage of a simulation you might be in, then if you put those variables into, say, a Python dictionary, then you can, there are a lot of like one line of code solutions for writing a Python dictionary out into a JSON file, and then you can load that JSON file back in when your program starts up. Compared to having the variables float around and not be in a dictionary, they're just traditional programming language variables that are in memory. There's no easy way to corral all of those up and save them to a file on disk. So in general, I think it's like, even if you're not using spot instances, I would make the pitch that designing programs to be checkpointable is like a very good practice and sort of fun if you like thinking about that kind of thing. And the approach that you're looking for is you want to be able to very clearly state the state of your program at any given moment so that you can crystallize it into a written description that's saved to the disk. Yeah, question.
It's about having the checkpoints. So if I'm saving things constantly, wouldn't that get in conflict with things like parallelization or threading?
It's a really good point to bring up. Thank you. So the question was, if you are saving things to disk constantly, then can this interfere with things like parallelization or just performance in general? And so there's definitely a balance that you need to strike here. I would say that the way that checkpointing systems generally work is that things don't get saved to disk until like some sort of like long time scale periodic event. And when I say long time scale, I mean in like the human range of like seconds to minutes to maybe even hours. So like a machine learning algorithm won't checkpoint until it's reached the end of some training epoch. In terms of code that you are writing, I would say, because you do get advanced warning about when you're going to be preempted from a VM, you don't have to checkpoint at all until you get an alert that you are going to be kicked off. And then as long as your code will run within 30 seconds, you're good. So you don't need to write anything to disk until you know that you're going to be shut down. Something else I was going to say. What was it? Yeah, I mean, I think that there's a lot of latitude to play with different things here. Oh, right. I remember the thing I was going to say. The reason why you might want to think about designing these things, even if they degrade performance, is because if performance is already bad, then when your code crashes, it's nice to be able to resume from an earlier checkpoint. I knew someone that was doing a lot of image processing with ImageJ, and ImageJ kept crashing. And one of the biggest things we were able to do to help this poor person was to help them figure out how to resume the job from like where the crash happened rather than at the very beginning of the image processing pipeline. And that involved saving data out to disk, and they needed to make sure they had enough disk to save that data, but it really helped their workflow so that it didn't have to like restart when things failed. Worth thinking about. Thank you for the questions, everyone. All right, so now to talk a little bit about storage. This is a very computation heavy tutorial. I don't talk that much about storage, certainly not as much as it deserves. But just as a quick overview of the options we have. So when we were talking about virtual machines having hard drives, what we're talking about is called block storage in Cloudland. In AWS, it's called EBS. In Azure, it's called disk storage. And this is the most expensive form of storage you can get because you're effectively reserving a hard drive. You are saying that the cloud provider cannot cut any corners or like secretly store other people's files on the same disk at the same time. They have to provide to you this notion of a hard drive plugged into your virtual machine that cannot be shared. So because of that, this is the fastest and most performant kind of storage. Usually you have only one per virtual machine, and it's in the 4 to a couple hundred gigabytes range. We're not talking a terabyte of data here. You can get block storage in the terabytes range, but this is very not cost effective. For that, we would usually recommend people use file stores, which you can think of as sort of analogous to like the network drives that you might have access to at your university. Or in the Jupyter Hub that we have for NeuroHackademy, it's like your user folder that you can store files in when you're, shutting your hub down for the day. So this is an order of magnitude cheaper than block storage, and it still behaves more or less like block storage does. So it still looks like a folder that you can access on the virtual machine. The performance is lower. So you'll find that if you have to do a lot of file operations, so if you're loading a lot of small files, then that might be slower. The same way that if you ever try to access a lot of small files on a USB thumb drive, it's much slower than when all those small files are directly on your laptop. So the pattern here is usually you get the files you care about from file storage and you load them onto your smaller block storage that's attached to the virtual machine itself. But the cloud-centric way of doing this, and the way we want people to get used to thinking, is in terms of object storage, which is really cheap, can effectively store as much data as you need, and is broadly supported by not just cloud providers, but there are like object storage interfaces for like personal hard drives now. So this is an increasingly common way of dealing with large data sets. And the idea with object storage, the thing that makes it weird is that it doesn't look like a folder on your computer, or at least it didn't used to. They're making tools these days that make it easier to use. But the way that we think about object storage is very similar to the way you might think about, say, Google Drive or Dropbox, where you upload a file or download a file from the web interface. So you work with individual files at a time. You say, I care about this 3 gigabyte MP4 video. I'm going to upload it or download it. And so a day in the life of a data set that uses object storage might be we have our full data set stored in the cloud in an S3 bucket. So in AWS's object storage. We take the files we care about and we download them using a little snippet of Python code or using a command line utility that we would type into a terminal. Then we run our code that deals with those files, and that code produces some output. And at that point, we upload the output, the results of our code, back to object storage, and we delete everything from the folder on our local computer. So we load what we care about, we operate on it, we save our results to object storage, and we delete it. And the way that we load and save files to object storage is effectively with a command. You could run that command in a terminal, you could run it in a Python script, or in a C++ program, but it's programmatic API access. That's how programmers would refer to this. And so object storage is the name of the game. A lot of big data sets usually have code written for you that can access the data set from object storage without you having to really think about that. This is where I would normally know the name of such data sets in the neuroscience community, but I've been working with oceanographers and climatologists and glaciologists for the past 3 days because we have another hack week going on. So I don't have any of those names in my head.
So the Human Connectome Project, the Natural Scene data set, these are all on S3 object storage. In fact, we'll be showing you a whole bunch of these on Friday in the data showcase.
Yeah.
Sorry? UK Biomech, yeah, there's a bunch more. It's not just those.
And so the way all of these did, thank you, Noah. And so the way that all of these data sets are able to be stored in the cloud cost effectively is by using object storage, which can do all sorts of like cost saving optimizations. Like if there's a file that no one ever needs, then it gets put into storage that takes longer to retrieve the file, but it's much cheaper. At a certain point, I think there are some hard drives in a basement and they have a tortoise that's really well trained that can go back and forth and like get them for you. But actually there are literally physical drive transfer services for object storage. It's called Glacier storage for the stuff that really it's archival. You want to keep it, but it might take you like a few days to a week to actually get it. And that can be really, really cheap, but not practically useful if you're actually using it to do work. Option is there. That's why we like object storage. So now getting a little bit into the different workflows here beyond just object storage. So the way that we most often use the cloud, especially when we're first starting to learn it, is by sort of interactively using the computer in the cloud, the same way I use my computer interactively on this podium. I actually found out it's not, a podium is the place at the front of the room and the lectern is the physical thing. The same way I use on my computer this lectern. So the idea here is that we have a laptop that is actually on our lap, and then we have a virtual machine in the cloud that is sitting next to our data set that we want to play with. And the way that we access that virtual machine is by logging into it remotely. And Jupyter Hub is a really nice and fluid way to remotely log into a virtual machine. There are other tools out there to do this, but the Jupyter Hub that we have access to in NeuroHackademy is a great example of a way that when you turn it on, you're turning on a virtual machine in the cloud and being given this interface to it that lets you run Python code or run Unix commands. And you do all of that through your web browser that you have open on your laptop. The place that this falls down is if you have code that you want to run when you are not physically connected to the machine, non-interactive computation. Oh, and I have some logos from services that provide things like this. I think this is like, this slide was from before when we provided Jupyter Hubs to people.
That would be before my time.
Yeah, or then it was like for anyway, once you leave NeuroHackademy, if you want access to virtual machines that sit next to major data sets, there are services like the Danby Archive for neuro stuff. Pangeo is something a bunch of geophysicists use. This is a very common pattern. But if we're talking about non-interactive data workflows, then there are a lot of other more complicated ways of accessing these virtual machines in the cloud. One that I learned about semi-recently is called Open On Demand, which is a nice web control panel interface that you can use to send code to any machine in a cluster of virtual machines, or even a cluster of machines with GPUs on them, with graphical processing units, which you can use to do machine learning and training jobs and things like that. And so this is just giving you a sense of like, usually the way you use the cloud is you log into something with your computer over a web browser or using a terminal. And then in a remote machine on the cloud end of the scene, you kick off some work to be done, either right in front of you interactively, or something that will cost more money on a more powerful computer that will then, when it's done, be given back to you in object storage and the computer shuts down. There are a lot of options here. And so when we talk about using the public cloud, this is really what we're talking about. We're talking about figuring out what size of a virtual machine you need and how to get your data and your code onto that machine so that it can do work that your laptop would not be able to do. And in all of those examples, I was talking about using a web browser through the Jupyter interface, which is nice and pretty and classy and doesn't require you to install any software on your machine, which is one of our favorite things about it as educators. But in terms of creating the machines and managing all of these virtual resources, there are a lot of different ways that we can interact with the public cloud. So the best way I think to get started learning this stuff is with web consoles. So in your web browser, you can go to like azure.microsoft.com, or is it portal.azure.com? Portal.azure.com. And they'll give you a control panel that says, hey, create a new virtual machine or delete a running virtual machine. A visual interface to show you all of the hardware you are renting and is costing you money. If you want to get more powerful with how you do these things, then there are command line interfaces, which are tools that you can run in a terminal on your computer or on a virtual computer. So I want to see if I have AWS's CLI installed in here. I don't remember. Do I have AWS on here? Oh my. Okay, let's try going into WSL. Do I have AWS on here? Nope. Do I have Azure? Oh God. So there are terminal utilities that you can run so that you can like say AZ create virtual machine. I'm like improvising this. This is not what it ends up looking like, but this is the type of interaction we have with the cloud. The reason why you might do something like this is because if you need to automate a task, then using a command line interface means that you can write a script that does it for you. So I was teaching a cloud computing workshop to a bunch of grumpy IT people. I'm actually realizing this is going to be recorded and posted on YouTube. So I need to like be clear that they were very like, honestly, like no sarcasm. They were extremely sweet. And it was one of the most fun things that I've ever done. Anyway, I was teaching a workshop for a bunch of IT people. And at the end of the day, they had created their Jupyter hubs. They went home, they were having fun. And I needed to delete all of the Jupyter hubs so that we would stop spending the money it costs to run 30 Jupyter hubs, which is not nothing. And the way that I ended up doing that was by writing a script that ran a CLI command to delete each of the things they created, and then looping over all of the different users that were in the workshop so that I could do that 30 times without having to manually click each thing in the browser window. That gets really useful. And if you don't want to use terminals, you can also write Python code or write R code that interacts with the cloud in this way. So there are SDKs and libraries for dealing with cloud resources. The place that this is most useful is for object storage. So there is a Python library that lets you load and save files from object storage very, very simply, the same way that you would load and save a file on your hard drive. And then the last thing that I want to bring up here is infrastructure as code, which is a way of sort of, it's like CLIs are commands in your terminal for interacting with the cloud. SDKs are like Python libraries for interacting with the cloud. People have come up with their own custom programming languages for describing what your cloud infrastructure looks like. These are things called like Terraform is the most popular one. But each of the clouds has their own brand name for these things. Useful if you're an IT department, less useful if you're an individual researcher. And also this is the slide where I mentioned this early on, where people will try to get access to your cloud account to mine Bitcoin. The place you need to be really, 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 really careful with And I'm emphasizing this because one of the functions of my job is to deal with the fallout when people are not careful with this, and people are never careful with this, is if you are writing Python code that deals with cloud things, if you accidentally put your password or your access key into that code, say in a Jupyter notebook, and then you add that notebook to a Git repo and you publish it to GitHub, suddenly your password to your cloud account connected to your credit card is on the internet. And there are people who have written very efficient bots that scrape GitHub for those keys so that before you even know it, they can spin up as many virtual machines as Amazon will let them, and they will mine Bitcoin. That is the thing. I'm not even like saying mine Bitcoin as like a glib joke. Like that's just literally what they want to do, is they want to mine Bitcoin because it's very cost beneficial. Yeah.
I just want to add for anyone who is not in my GitHub section history anyway, that as a reminder, once you've committed something to GitHub, it's really hard to uncommit it or to get it out of GitHub. So even if you revert it, it's still going to be in the history. And so this is part of why it's very dangerous. People will commit it and then think they've gotten it out. It's not.
Yeah. Yeah. So it's hard to scrub things from Git history. It's easy to accidentally have passwords be retained in Jupyter notebooks when you don't realize it, because like sometimes the output to a cell is cached, even if the output is not visible on your screen anymore. Kind of a nightmare. So when you're first starting to use the cloud, if you're using the web browser interface, you have nothing to worry about, and you do not need to sweat bullets about this. If you are writing Python code that creates and deletes cloud resources, you need to be really careful about that. And you can talk to me offline or Noah offline if you want to get the actual lecture about how to do this securely. I don't really want to bring up our methods for doing so now because I feel iffy about bringing up a really sensitive security thing without enough time to do it justice. But basically, at all costs, figure out how to not put your password physically into code that you write. Find some other way to get access to the resources you need. Okay, so to round out our day, I want to talk a little bit about the sort of organizational structures that all of this stuff is contained within. I have a prompt. I will not subject you to the prompt because we don't have that much time left. But I spent a while photoshopping these Matryoshka dolls into this slide, so let's just appreciate how cute they are. So I'm asking you how you organize things because I am about to show you how Amazon and Microsoft organize things. So on Azure, and basically, I hope you can take these slides with you if you ever need to use these cloud platforms and just use these to figure out what the heck is going on. So in Azure, there is an Active Directory that by necessity, if you are on Azure, you are in a directory somewhere. It might be Microsoft's global Active Directory. If you are doing anything with University of Washington people, UW has an Active Directory. This is the same directory that like stores people's Outlook email addresses and stuff. And so in general, there's one per institution. UW has one. It's managed by IT, and we don't have that much control over it. Within an Active Directory, there are subscriptions. And a subscription is the unit of organization in Azure that actually pays for things. So if you have to enter credit card information, you enter it into a subscription. And within a subscription, there are resource groups, which are lightweight ways of organizing the virtual machines and disks that you have. And inside of that resource group is the machine that actually does the computation. So the general workflow here is that if you are in a lab, your PI will give you access to their subscription. Within that subscription, you will create a resource group to put all of your things, and then you will create and delete the stuff that you actually use in the cloud. That's just for Azure. For AWS, we have actually fewer organizational structures. So AWS has something called an account. And the idea here is your PI will create a cloud account and they will provide their billing information in that account. Each account comes with a root user, which can do anything. It's strongly suggested you don't log in as the root user to an AWS account. Instead, there are sub-users, IAM users, and IAM roles. They're technically different things, but they're basically synonyms. And the idea here is that the root user is only there so that they can create IAM users. And the IAM users are the user accounts that you actually log in with and use to create virtual machines and delete virtual machines. And optionally, AWS has this notion of organizations. So UW has a few different AWS organizations, though they're not as integral a part of the organizational infrastructure as they are with Azure. And so the big takeaway I want on this slide is that if you ever sign up for an AWS account, then by default, you're logged in with the root user. And what they really, really, really want you to do is go to the IAM tab in your web browser and create a sub-user for yourself. And that is what you should actually log in with forever after. And then finally, just to round out the discussion with GCP jargon, GCP has projects, which are sort of like AWS accounts and like Azure subscriptions. A GCP project is like what you would use, probably one per lab. You could hypothetically have a project at a smaller scale, say for one paper or experiment, but usually the way I've seen it used is that a PI will create a project for their lab, and within that project, they can create virtual machines, and they have a billing account that is connected to that project. So that billing account can be connected to many projects. So they'll create a billing account with their credit card, and then they'll create a project that all of their grad students can log in with. And then again, optionally, there is this notion of organization that all projects within an institution can fall under, but again, not as integral as the way it is in Microsoft land. And so I guess the last thing that I really have time to cover here is just talking about which platforms you should choose, because this is a real question and it's a good question to ask. And there isn't a particularly good answer to it, partially because they're all more or less as capable as each other. So I think that when asking which platform you should use, you should look at what your colleagues are using and what they've used in the past, because they're the people that are going to be able to help you get unstuck. And if there are collaborators online that have written code that runs in the cloud before, they will have written guides that help tell you how to do things. Also, if you have data sets that you know are available in a given cloud, say Azure is presenting a given set of MRI scans, but AWS has a bunch of like information about neural flimflams or whatever. Like, if you choose the cloud that has the data set you want, then it can be a smoother and easier experience. I think in practice, there are easier and harder things to do on all of them, but I've very rarely encountered something that I can do on one that I cannot do on another. And all of those things fall under the umbrella of things that the people in this room really would not want to worry about. Specifically, I will say that, like, if you want to create a Kubernetes cluster, you need owner level permissions for a subscription on Azure. You do not need that on AWS, which means that you need to give people the keys to the kingdom to create a scalable computer cluster on Azure, but you do not need to give people keys to the kingdom to do so on AWS. That's not a hard and fast rule. There are ways to create clusters that don't involve Kubernetes. This is why it's not relevant. Don't worry about it. You can do whatever you need on any of these clouds. So it's 5 p.m. I have some meta discussions about learning to cloud, and they all basically fall into the category of there's a lot to learn. Don't worry about it. Focus on your science. Get a minimum viable example of how to run your code in the cloud, and that is more than most people will be able to do. You start iterating from there. Also, you will have the opportunity to set all sorts of settings and configuration keys and stuff. Most of the time, the defaults in these control panels and wizards will work fine for you, and you don't need to know what each item does when you're creating a virtual machine. Most of the things are set up to just work. And finally, if you're banging your head a lot, find someone that knows more than you do and ask them for help, because you can really spend a lot of time trying to get this stuff to work. Mostly, I just love this GIF. I wanted to include this GIF. I also have a link to a demo. The demo shows us how to set up a Jupyter Hub. And I encourage you, if you're at all interested in this stuff, to try it out, because if you sign up for Azure and you have an edu email address, you get $100 in credits and funny money. And this is a tutorial that I wrote that is relatively up to date about how to set up a Jupyter Hub on Azure. And I'm happy to field questions if you guys do this after this tutorial. Be in touch with me. I'll be on Slack. And also, this is my email address. It's been a pleasure. Thank you all for spending your Wednesday afternoon with me.